Hello students, in this video I would like to discuss about analysis of recursive procedures. Recurrence relations. Running time of recursive procedures are expressed using recurrence relations. So to analyze a recursive procedure, first thing is you have to denote that the running time of recursive procedure in the form of a recurrence relation. Later by solving that recurrence relation we will get the complexity of that procedure. So here I have a procedure to find factorial of a number. You are all familiar with this procedure. So we are going to find factorial of n. So you just consider t of n be the running time function to find factorial of n. Then what will be the running time function to find factorial of n minus 1? It will be t of n minus 1. So what's the meaning? The time to find factor of n is t of n, then the time to find factor of n minus is t of n minus 1. So you just come back to a procedure. Just look at this one. Line number 2 only needs a constant time. Line number 3 also needs a constant time. Line number 4 also needs a constant time. So how many times this procedure will be called? n minus 1. So what's the time to execute n minus 1? It is t of n minus 1. So I can write the recurrence relation as t of n equal to t n minus 1 plus c. So what's the meaning? The running time of factor of n is running time of factor of n minus 1 plus some constant. And it means the running time of factor of n minus 1 is running time of factor of n minus 1 plus c. So why this c? Because some more lines has to be executed. It takes the constant time, so it is c. So c denotes execution time of line number 2, 3 and 4, which is constant. So what happens when this value of n is 0? It will execute these two lines, 2 and 3. So at that time the running time is the constant. So the only value we know is when the input is 0, the running time is a constant. So we have to represent this running time of factor of n as a recurrence relation. T of n equals c when n equals 0. In other values, when n greater than 0, it is t of n minus 1 plus c. So there are three methods to solve recurrence relations. First one is back substitution. Next one is recurrence tree method, and the third one is Master's theorem. In this video, we are generally discussing only about back substitution. This is the first example of back substitution. I will try to explain back substitution with the help of this example. So here was the recurrence relation, t of n equal to t of n minus 1 plus c, t of 0 equal to c. This recurrence relation denotes running time function to find factorial of n. So t of n equal to t of n minus 1 plus c. So here I have t of n minus 1. We just find t of n minus 1. How will we find t of n minus 1? Just substituting n minus 1 in the given equation. This is the given equation. So t of n minus 1, t of n minus 1 equal to, in place of this n I am substituting n minus 1, n minus 1 minus 1, that is n minus 2 plus c. So again I am substituting this back to our equation. So in place of this t n minus 1 I am going to substitute t n minus 2 plus c. So it is t of n equal to t n minus 2 plus c plus this c, that is 2c. Similarly I am going to find t n minus 2. How will I find t of n minus 2? I will substitute n minus 2 in place of this given equation. t n minus 2 equal to t n minus 2 minus 1, that is t n minus 3 plus c. So in place of t n minus 2 I am placing this expression, t n minus 3 plus c plus 2c, that is 3c. So I will continue that step. At some point I will reach the kth term. So what is the kth term? So I will generate some patterns and I will write the relation for k term. It will be t of n equal to t of n minus k plus kc. So it is in this place of 3 I am just writing k. So t n minus k plus kc. So when this recurrence relation will terminate. The recurrence relation will terminate when this term becomes 0 and this becomes t of 0. So at some point it will become t of 0. So when it becomes 0 and when n minus k is 0, what's the value of k? K is n. So this will terminate when n minus k is 0. When n minus k is 0, k is n. So this I can write it as t of 0 plus, since k equal to n, I can write it as nc. You all know the value of t of 0, it is c, plus nc. Just discarding the constants and coefficient of higher order term, you will get the complexity as t of n equal to O of n. We will see more example. So the next recurrence relation is t of n equal to t of n minus 1 plus n and t of 0 equal to 0. First, you just write the given equation. Then you have to find t of n minus 1. How to find t of n minus 1? Just substitute n minus 1 in the given equation. So t of n minus 1 equal to t of n minus 1 minus 1, that is t of n minus 2, plus in this place of n also you have to substitute n minus 1. So it becomes n minus 1. So t of n can be written as t of n minus 2 plus n minus 1 plus n. Then I will find t of n minus 2. How to find t of n minus 2? Just substitute n minus 2 in the given equation. So you will get an expression like this: t of n minus 2 equal to t of n minus 3 plus n minus 2. Just substitute back here. That is t of n minus 3 plus n minus 2 plus n minus 1 plus n. I will write one more term. So this is the pattern I have generated. Generalize this one in terms of k. T of n equal to t of n minus k. Now how will I write this term? N minus k minus 1, because this is n minus 4 minus 1. How will I write this term? N minus k minus 2, because this is n minus 4 minus 2. So this is the generalized term. So it will reach n minus 3, n minus 2, n minus 1 to n. And it will terminate when n minus k becomes 0, it will terminate. So when n minus k equals 0, it will terminate. When n minus k, the k value is n. So n minus k, and just expand this expression n minus k plus 1, n minus k plus 2 up to some n. So this will terminate when n minus k becomes 0. So it is t of 0 plus, in place of this n minus k I am substituting 0, so it will become 1. Here also I am substituting 0, it will become 2, and some point it will reach n minus 3, n minus 2, n minus 1 up to n. So it is nothing but sum of first n terms. So t of 0 I can write it as 0 because it is given. This is written as n into n plus 1 by 2. So the higher order term is n square. So the complexity of this procedure is O of n square. Okay, next look at this example. Here the recurrence relation is t of n equal to t of n minus 1 plus n square. So we will rewrite the equation. We will find t of n minus 1 by substituting n minus 1 in this equation. So t of n minus 1 equal to t of n minus 2 plus n minus 1 whole square. Substituting this back, we will get an expression like this. Here I will find t of n minus 2. How will I find t of n minus 2? Just substituting n minus 2 in the given equation. T of n minus 2 equal to t of n minus 3 plus n minus 2 the whole square. Just substituting this back and generating some patterns. Again we are generalizing in terms of k. T of n equal to t of n minus k plus n minus k minus 1 the whole square. And it is 4 here, it is 4 minus 1 here. So it is k minus 1 the whole square, and k minus 2 the whole square, and n minus 3 the whole square, n minus 2 the whole square, and minus 1 the whole square, and n square. So just expanding these terms, you will get t of n minus k plus n minus k plus 1 the whole square, minus k plus 2 the whole square, up to some n. We all know this recurrence relation will terminate when n minus k becomes 0. So when n minus k becomes 0, k equal to n. So at some point this term becomes t of 0, it is t of 0. At that time, what will be this term? N minus k is 0, so it is 1 square. Here also n minus k is 0, so it is 2 square. So 1 plus 2 square up to some n square. that is sum of squares of first n terms. So the formula to find sum of squares of first n terms is n into 2n plus 1 into n plus 1 by 6. So it is n into 2n plus n, 2n into n is the higher order term. So discarding constants and coefficients, you will get complexity as O of n cube. Another example, here the recurrence relation is T of n equal to T of n minus 2 plus 1 and T of 1 equal to 1. So when the input size is 1, the running time is 1. That's the base condition. So what's the meaning of this recurrence relation? I have a recursive procedure. The time taken to calculate input of size n is time taken to calculate half the size plus 1. That's the meaning of this recursive procedure. So I am rewriting this expression T of n equal to T of n by 2 plus 1. So I am going to find T of n by 2. How will I find T of n by 2? I am just substituting n by 2 in the given equation. That is Tn by 2 equal to Tn by 2 by 2, that is Tn by 4 plus 1. So I am substituting this back here. T of n equal to T of n by 4 plus 1 plus 1. After writing this line, I am going to find Tn by 4. Tn by 4 equal to this. How to find Tn by 4? Just substituting n by 4 in the given equation. It is Tn by 4 equal to Tn by 4 by 2. It is n by 8 plus 1. So I am substituting it back here. So I get T of n by 8 plus 1 plus 1 plus 1. So how this term will be written? T of n equal to T of n by 2 raised to 1 plus 1. This 4 can be written as 2 square. So T of n by 2 square plus 2. So this 8 can be written as 2 cube. So here it is T of n equal to T of n by 2 cube plus 3. So after some point I will write the generalized term. So how will I write? So I will write the kth term here. T of n equal to T of n by 2 raised to k plus k. So at some point this n by 2 raised to k becomes 1 because that is the base condition. N by 2 raised to k equal to 1, that is 2 raised to k equal to n. Take log on both sides, k equal to log n. So at some point it will become 1. So it is T of 1 plus k in terms of n is log n, so it is plus log n. So we all know T of 1 is 1 plus log n. When I represent in terms of asymptotic notation, it will become, example 5, T of n equal to 2Tn by 2 plus 1. And the base condition is T of 1 equal to 1. So I am writing this equation. So I am finding T of n by 2. So how to find T of n by 2? By substituting n by 2 in place of n in the given equation. Tn by 2 equal to 2Tn by 4 plus 1. So I am substituting it back. Tn equal to 2. In place of Tn by 2 I am writing 2Tn by 4 plus 1 plus 1. So I am multiplying it. T of n equal to 4 Tn by 4 plus 2 plus 1. I am finding Tn by 4. How to find Tn by 4? Substituting n by 4 in place of n in the given equation. I will get Tn by 4 equal to 2Tn by 8 plus 1. I am substituting it back. 4 in place of Tn by 4 I am substituting 2Tn by 8 plus 1 plus 2 plus 1. So I am multiplying 4. T of n equal to 8 Tn by 8 plus 4 2 plus 1. So similarly I will find T of n by 8 and I will substitute back. I will get an expression like this. So how I can write this expression? This can be written as 2 raised to 1 Tn by 2 raised to 1 plus 2 raised to 0. Similarly this can be written as 2 square Tn by 2 square plus 2 raised to 1 plus 2 raised to 0. This can be written as 2 cube Tn by 2 cube plus 2 square plus 2 raised to 1 plus 2 raised to 0. And this can be written as 2 raised to 4 Tn by 2 raised to 4 plus 2 cube plus 2 square plus 2 raised to 1 plus 2 raised to 0. So I am generalizing this term as a kth term. So here I will write T of n equal to 2 raised to k Tn by 2 raised to k. This 2 raised to 3 is same as 2 raised to 4 minus 1. So I am writing it as 2 raised to k minus 1 plus some 2 cube plus 2 square plus 2 raised to 1 plus 2 raised to 0. So what is this term? What is this term? 1 plus 2 plus 4 plus 8 up to 2 raised to k minus 1. This is 1 plus 2 plus 4 plus 8 plus 16 up to 2 raised to k minus 1 equal to 2 raised to k minus 1. So the sum of the series is actually 2 raised to k minus 1. So I will try to explain the sum of the series with these three terms. What's the sum of these three terms? 7. This term can be written as 2 square. So what's the next term? 2 square plus 1. That is 2 cube minus 1. 2 cube minus 1 is 7. Similarly here, what is the last term? 2 raised to k minus 1. What is the next term? 2 raised to k. So the sum of this entire term is 2 raised to k minus 1. So it is written as 2 raised to k minus 1. So at some point this n by 2 raised to k becomes 1. So at some point this n by 2 raised to k becomes 1. At that time 2 raised to k equal to n. So taking log on both sides, k equal to log n. So in place of this 2 raised to k, I am substituting n. In place of this t n by 2 raised to k, I am giving it as t of 1, since this n by 2 raised to k is 1. And this 2 raised to k is written as n. It is actually n into 1 plus n minus 1. That is n plus n minus 1. So the higher order term is n. So the complexity of this entire procedure is O of n. So one more example, it is t of n equal to 2tn by 2 plus n. And similar to the earlier examples, I found some subterms and substituted back. So I will get some patterns. From that pattern I am generalizing in terms of k. T of n equal to 2 raised to k, t of n by 2 raised to k plus kn. So the base condition here is t of 1 equal to 1. So at some point this big terms become 1. At that time we will get the value of k as log n. So n into t of 1 plus this k becomes log n, this n is also there. So we will get n plus n log n, which is a lower order term, so just discard it. So the complexity of this procedure will be n log n. Let's look at example 7. Here I have a question to find complexity. Here I have a recursive procedure called rec. So rec of n equal to, if n equal to 1, return 1, else return rec of n minus 1 plus rec of n minus 1. So here this is the base condition, t of 1 equal to return 1. So it will be constant. Constants can be represented as O of 1, we already studied. And this writing 1 here, 1 of that O of 1. And otherwise, if n is not n, it will return rec of n minus 1 plus rec of n minus 1. So what's the meaning? It is I am following rec of n minus 1 2 times. Rec of n minus 1 2 times. So I can write a recurrence relation like this. T of n equal to 2tn minus 1, since rec of n minus 1 is called twice, plus 1 for these constant time execution lines. So the recurrence relation can be written as t of n equal to 2tn minus 1 plus 1, and the base condition is t of 1 equal to 1. So the same procedure is applied here. Some terms are found by substituting, after that I am just generalizing. So it will terminate when n minus k equal to 1, and that time k equal to n minus 1. So the same procedure in the earlier example is applied here. In the end I will get the complexity as O of 2 raised to n. So this is all about back substitution. Thank you.